to acid-base reactions. So remember that precipitation reactions are double displacement reactions. Acid-base reactions are as well. Okay. So what does that mean? You guys already know what an acid, how to spot an acid, right? It starts with H, right, which is the proton, H plus, and then followed by, an anion, either a monatomic anion, which is a binary acid, or a polyatomic ion, and those are called oxoacids, right? So acid-base reactions is when an acid reacts with a base to form water and a salt. So basically, it's called a neutralization reaction because the acid and the base cancel out. Okay. Now, bases are really easy to spot too. They are hydroxides. Okay, so anything hydroxide is considered a base. Okay, so you guys may have heard of sodium hydroxide, right? That's a very common base, but you also can have potassium hydroxide, lithium hydroxide. All of those are bases as well. Okay, so when bases and acid react, right, they cancel each other out and they make neutral water and then the corresponding salt, right? A corresponding ionic compound. So that's why it's called neutralization, because water is formed. Okay? So gas evolution reactions, this is, not necessarily a separate class, but it's just when any reaction produces a gas. And so a lot of acid-base reactions are also gas evolution reactions as well. Okay. So that's all that that is. Okay. So let's remind ourselves, right? What is an acid and then what's a base? So the Arrhenius definition of an acid, and Arrhenius is basically the grandfather of acid-base chemistry. And he first defined an acid as any substance that produces H plus in water, right, in an aqueous solution. So, something like HCl, okay, and you can tell that this is an acid, right? It leads with H, produces H plus, right, in water, and Cl minus. So it looks very ionic, doesn't it? A cation and an anion, right? So acids, you can kind of think of them as ionic because the proton is charged, right? It's positively charged. So now the proton doesn't just stay there by itself. It's quite reactive. So it will get picked up by water. It actually binds to water to form what we call the hydronium ion, right? H3O plus. And this is one of your polyatomics that you should know too, right? So a hydronium ion is just basically an H plus with a water attached to it, right? So there are some acids, so HCl, right? We call this a monoprotic acid because it only has one proton, right? Remember H plus is called proton. So it's a monoprotic acid because it can only release one proton. However, you have polyprotic acids as well, and these contain more than one ionizable proton, and they get released sequentially, right? So something like H2SO4, right? H2SO4 has two protons that can be released, right? And why is it H2SO4? Well, SO4 is 2 minus. Remember, that's sulfate anion. And so you need two protons to balance it out, right? So that's why we call them polyprotic acids. So they have multiple protons that can get released, okay? So again, right? Arrhenius definition says an acid is going to produce an H plus in solution. Okay, so then what is a base? Arrhenius defined a base as any substance that has OH minus ions, that can produce OH minus ions. And those are hydroxides, right? So as I mentioned, if you see a hydroxide of any sort, it's going to be a base, right? So sodium hydroxide and OH minus, right? And Na plus comes together. So it will dissociate into Na plus and OH minus. Okay, so when an acid and a base comes together, we call these neutralization reactions. Okay, so let's take a look at this first one here. We have HNO3 aqueous, right? Two of those, plus CaOH2, that's calcium hydroxide aqueous, to form calcium nitrate aqueous and to water. It's a balanced equation, right? So notice how that works. Your acid here is nitric acid. And so the proton is H plus, right? And calcium hydroxide has OH minus in it. So think about it. And the H plus and then the OH minus makes what? H2O, right? H plus and OH minus. And then what's the other couple? Calcium and nitrate. So do you guys see how this is a double displacement reaction, just like a precipitation reaction, right? It swaps partners, right? So the cation here goes with a new anion, and then this cation, Ca2 plus, goes with the new anion nitrate, right? To get calcium nitrate. So the mechanics is the same, which means you guys should be able to predict the products of acid-base neutralization reactions now as well, right? So you always do the double displacement first, and then you balance the equation, right? And what you'll find is when you write the complete ionic equation and then the net ionic equation, the net ionic equation will always be the same. It's the proton and the hydroxide coming together to make water liquid. Okay, that is the net ionic equation, right? And then the salt will just, be whatever salt that you know, had started with, right? So here's another example, right? You have HCl, that's hydrochloric acid, and sodium hydroxide, that's your base. And what happens? The proton, the H plus, goes with the OH minus to form water, which is liquid, right? And then what's left over, the sodium is going to go with the chloride. And since sodium is plus and chloride is minus, it's just 1-to-1, right? Sodium chloride aqueous, right? And subsequently, like accidentally, the equation's already balanced here, right? And so we're good. Okay. So here's just an illustration of this neutralization reaction between hydrochloric acid and sodium hydroxide. Notice that they are both aqueous, right, to begin with. So they're in their separate test tubes here. Here's the HCl, here's the NaOH, right? When they are poured together, they form water and sodium chloride. So what's happened here? Well, why is it called neutralization reaction? Well, would you drink hydrochloric acid? No, you can't, right? It would damage you badly. And you would not drink sodium hydroxide either, right? You would not just go like that. However, if you put them together, right, now you can drink the products. It's totally fine. You drink this every day, right? Salt water. Okay. So we know a reaction has happened, right? Because the acid's no longer acid, the base is no longer there either, right? It has neutralized, they cancel each other out. And basically you just have water left, right? And the corresponding salt. All right. So on this slide here, it lists some common acids and bases for you guys. Notice, they all the acids, they start with H, right? These are the strong ones here, and then the weak ones are in pink. Okay. The base, notice they all end in hydroxide, right? So that's how you're gonna spot it, right? That's how you're gonna spot it. So now you know two reactions, right? You know precipitation reactions, acid-base reactions. They're both double displacement, right? But how you gonna tell between one or the other? Well, look for the H in front, right? And look for a hydroxide. Then you know it's an acid-base reaction. If you just have a normal ionic compound with another ionic compound, then most likely that's gonna be a precipitation reaction, right? So always look at your compound first and try to identify what it is, right? Classify it first. Oh, that's an ionic compound. Okay. Oh, and now it's going with another ionic compound. So it's probably precipitation reaction. Oh, but here, you have H in front. Oh, so that's an acid. Okay. Are we reacting with a base? Is there an OH there? Is there a hydroxide? Oh, there is. Okay. So then it's a neutralization reaction. Right. All right, so let's switch to the board and we're gonna practice some more with predicting acid base products. It's just again, right? Double displacement, but let's practice, okay? So acid base neutralization reactions. It will always form water and salt. Okay, that's the mark of a neutralization reaction, right? That's why it's called that. So let's do a couple examples here. Let's do hydrochloric acid and barium hydroxide. So hydrochloric acid, aqueous, right? You guys know the name now too, right? Hydrochloric acid, you should be able to generate that. And barium hydroxide, you should generate that too. Barium is 2+, hydroxide is minus. So BaOH2. Okay. And now, remember, it's double displacement, right? We know this is plus and this is minus. And if this is helpful to you, write the charges on top, okay? Just as like a bookkeeping thing. Barium is in group 2A, so we know it's 2+. Okay? Each hydroxide is negative, right? That's why we need 2 of them, okay? But now that's going to help us, right? So the H plus is going to go with the OH minus, right? They're going to swap partners. Of course, the H plus can't go with barium, right? Because cations are not, right? They're both the same charge. They repel each other. So the plus must go with the minus. What's H plus and OH minus? Water. And what state is water? Liquid. Okay. Plus, barium is going to go with chloride. But since chloride is only negatively charged, like 1 minus, right? And barium is 2+. How many chlorides do we need? 2. So it's BaCl2. Okay. Then we look that up on our solubility chart, right? Remember, like anytime you had ionic compounds now, you can look up on your solubility chart so that you can write the state. And you'll find that it is soluble. So remember, we're going to write aqueous. Okay. All right. So that's the first step, right? It's just predicting the products. And then after that, we got to balance the equation. Okay. So put your hand on the most complex. It's looking like this one. Okay. My bariums are balanced. I have 4 hydrogens on this side, right? 2, 3 actually. Okay. Let's do the oxygen first then. 2 oxygens on this side. There's only 1 oxygen here, so I'm going to put a 2 there. Okay. And so now I have to balance my hydrogens, right? On the left side, I have 3 hydrogens. On the right side, I have 4. So how do I get 4 hydrogens on the left side? Well, let's just put a 2 there. So I get 2 hydrogens here and 2 hydrogens there. And now also balance my chlorides, right? 2 chlorides on each side. Okay. All right. So this we call the molecular, right? Equation. Let's practice writing our complete ionic. Okay, so remember, y'all, for complete ionic, anytime you see AQ, I'm gonna split it apart, right? I have 2HCl here, so I'm gonna write 2H plus aqueous plus 2Cl minus aqueous plus barium is 2+. See, it's kind of useful to write the charges on top, so you just have it right there. Okay, just figure it out and then write it down. And then, okay, pay attention to the coefficients, right? And also the subscripts. That's telling you there are 2 units of hydroxide, right? So that's 2 units of hydroxide. Okay. Those 2. Do we split this up, guys? No, right? Because liquid does not get split up. Only aqueous gets split up, right? And then, so aqueous, we split that up. Ba, we already know is 2+, right? Aqueous. And we had chlorides charge up earlier, 2Cl minus. And then for the net ionic, right? All I need to do is cancel things that occur on both sides. Okay, and barium. Chloride and barium. So what do I have left? 2H plus aqueous plus 2OH minus aqueous goes to 2H2O liquid. But notice these 2 can just get divided, right? Divide everybody by 2, so you end up with this. Okay. All right. And then you just need to put what the spectator ions are. It's the ones that you cross out. Ba2 plus and Cl minus. Okay. Makes sense, right? Okay, so you see how it looks just like last lecture when we did precipitation reactions, right? Doing molecular ionic, then ionic. Okay. Let's do another example. This time, let's do lithium hydroxide aqueous plus sulfuric acid, H2SO4 aqueous. Okay, goes to, okay, predicting the products, right? Remember, it's just swapping the partners, okay? Get the charges first. I think this is really gonna be key to making this a lot easier on you. Just get the charges first. What's lithium's charge? It's in group 1A, so it's a plus, right? Write that on top. What is hydroxide's charge? It's gonna be negative, right? You know your polyatomics. What is H charge? Well, it's a proton, right? So each H is a plus, right? We know that sulfate is 2 minus. We know our polyatomics, okay? So now, see, doesn't that just look easier to do? We got a plus here and we got a 2 minus here. That means I need 2 lithiums, right? So Li2 SO4. Now I got to look at my chart, right, to see if that is soluble or not. Okay, so it's a sulfate. We're going to look, okay, sulfates are generally soluble, and there are no exceptions for lithium. So, well, aqueous. Then plus, what's the other product? Well, the OH minus is going to go into the H plus, right? H plus and OH minus. And so that's going to make H2O. And we know that's a liquid. Okay. So as you can see, right? Always water and a salt. That's what a neutralization reaction makes, right? Water plus whatever corresponding salt. Okay. Next step, balance it, right? Okay. Put my finger on here, most complex. Balance the lithium first. I'm going to put a 2 in front of there. The sulfates balance. Okay, so I'll go over here. I need 2 oxygens. That's just 1 oxygen, so I'll put a 2 here. That's 4 hydrogens, and 2 and 2, 4 hydrogens on each side. Okay. All right, so now that that's balanced, I know that that's called a molecular equation, right? That's called a molecular equation. What if we want the complete ionic? Split up the aqueous, right? So 2 Li plus aqueous plus 2 OH minus aqueous plus. This gets split up too, right? And that's 2 protons there. 2H plus aqueous plus SO4, 2 minus aqueous goes to, this is aqueous, so we split it up as well. 2 Li plus aqueous plus SO4, 2 minus aqueous plus 2. Okay. And now we cancel things out that are the same on both sides. So what do we get? Sulfate is gone. Lithium is gone. And we have 2 for the net ionic, right? 2 OH minus plus 2H plus goes to 2 waters again. Okay. And see these 2's in front just get canceled, right? Or yeah, we just simplify it down, right? So OH minus plus H plus is water. Notice this net ionic equation is the same as the last one, right? So for all acid-base reaction, and the last one, right? Same. So all acid-base neutralization reactions have the same net ionic equation, right? Remember, that wasn't true for precipitation, but for acid-base it is. Okay, so spectator ions, SO4 2 minus, and Li plus. Okay. All right. So you guys go practice that, right? It's the same mechanics as the precipitation reaction, but the only thing here is, you know, you got to learn. I think you guys already know how to spot an acid, but now, right? The new thing is spotting a base. So if you see them together, you know it's an acid-base neutralization reaction. Okay. But if you just do double displacement, right, you'll figure it out. Oh, you're like, oh, it makes water, right? It has to go to make water, right? OH minus and OH plus. Okay. So just do the double displacement and you should be fine.